Hello, welcome back to our final unit, Unit 6. We are going to start talking about electric and magnetic fields together, and we're going to start treating them as waves. And that is going to be a pretty interesting set of discussions we're going to have. A lot of people find this to be like the most interesting maybe topic in the entire book. Probably because we use electromagnetic waves every single day to do our daily tasks, right? We can communicate near the speed of light because of electromagnetic waves. We're able to listen to music. We're able to, watch our favorite shows because of the fact that we can use electromagnetic waves to communicate, okay, at near the speed of light. So let's learn about how electromagnetic waves are generated, how the speed of light is related to certain fundamental constants that we will use to describe electromagnetic waves, how they propagate in space. We're going to talk about them briefly as plane waves, also as sine waves, the energy that electromagnetic waves carry, and also what happens if you stick some electromagnetic waves in a cavity, okay? For example, a microwave. So it's a brief introduction. We really don't need much introduction for this. We use electromagnetic waves every day. What you may not have known is that metal objects reflect electromagnetic waves. That's why when you go and get an X-ray, you wear a lead vest, and you might even, or if you're getting a CT scan or something, you're in a room that is lined in lead because those electromagnetic waves that they use to measure certain things in your body, they don't want those leaving the room. And so you line the room with metal, and that reflects the waves right back, keeps it in the room, okay? So same reason that microwaves are made of metal, okay? That's because you want to keep the microwaves in the microwave oven and not constantly radiating you and objects in your home when you're heating up food. So we'll talk about all these different kinds of electromagnetic waves and how they generally behave. And so you may want to go back to, I don't remember the chapter number, but where we talked about waves on a string, okay? Traveling waves. We're going to be using the same math to describe waves, okay? Except there's just going to be a couple of tweaks because we're talking about electromagnetic waves. One of those tweaks is that electromagnetic waves do not require a medium to travel. So traveling waves on a string, obviously you need a string there to get that wave to move through it. In electromagnetism, for an electromagnetic wave, it can propagate in vacuum, okay, like in space. That's, space is empty, right? The very little, very little particles in outer space, waves travel through them all day long. That's how we see stars, right? If electromagnetic waves couldn't propagate on their own without a medium, we wouldn't, the sky would be black. Okay, we would see nothing, and that would be really scary. So let's talk a little bit about kind of the mathematical source of this idea that electromagnetic waves can propagate without a medium. So here we have Maxwell's equations. Let me just erase this stuff. We have Maxwell's equations in vacuum, okay? And we may recall in the beginning of this course where we talked a lot about stationary E fields and stationary B fields. For example, a charge, producing an electric field, right? That's a stationary electric field that doesn't change in time. Or a current carrying wire, a DC current, and we're looking at one snapshot in time, and we can see where the B fields are. Eye pointing down, okay? So those are two situations of a constant electric or magnetic field, and we were able to treat all the fields independently. Well, when you get to fields that change in time, that's what the second set of Maxwell's equations kind of talk to you about, is here you have, right, inside flux, you have the dot product of the B field, dot product of the E field, right? If that changes with time, or in any way, right? Remember, B could change, A could change, cosine theta could change. But if there is any component of the flux that changes with time, you will be producing an electric field. If any aspect of the electric field is changing with time, you will be producing a magnetic field. And that is exactly how electromagnetic waves propagate in space, okay? You have something that creates let's say, how about a current, right? Let's say you have something like an electron that is moving around in an oscillatory fashion, producing a current that changes with time. Well, guess what? You're going to have a magnetic field that changes with time. And guess what? That's going to produce an electric field that will also change with time. And then because you have that electric field that's changing with time, that guy would go right here. He then would produce his own magnetic field changing with time. And then this cycle will continue. Okay? That's wave propagation. That's exactly how these electromagnetic waves propagate in vacuum, repeatedly, endlessly. And that's why we see light from distant stars. Okay, it takes a while to get here, sure, but nothing is interrupting its path here. Okay, vacuum, it just keeps rolling through vacuum, no big deal. Doesn't lose any energy because it doesn't encounter anything to lose energy to. So there's all sorts of different ways electromagnetic fields are created. All right. So one of them, obviously, that we've been talking about at length is currents that change with time. For example, the currents in a transmission tower, right? A transmission line tower. So you have currents flowing down these wires with time varying amplitudes. Okay. Well, that time varying amplitude will produce a time varying magnetic field. And then that time varying magnetic field will produce a time varying electric field. Okay. And then that time varying electric field will produce another time varying, and it goes on and on and on. Okay. So, moral of the story is anywhere that you have either a moving electron or a current, or anywhere that you can consider a time varying charge, you will be getting a magnetic field produced, which will produce an electric field, and therefore you have electromagnetic waves. So electromagnetic waves exist all around these wires, okay? They exist outside of atoms with electrons that are moving around in an oscillatory fashion. And they all, depending on the frequency at which they oscillate, that gives you a different type of electromagnetic wave. So here they all are. And so one thing that when these electromagnetic waves, when they're in vacuum, the one thing that they all share is the speed in which they travel, which is the speed of light. So even if it's not light that we're talking about, if we're talking about a radio wave or we're talking about an X-ray, if they're in vacuum, they will travel at the speed of light, okay? 3 times 10 to the 6 meters per second. And so if their frequencies given are, depend on the source, okay? The frequencies are depending on the source, they travel at c, then their wavelength is related to c like this, okay? Speed is equal to wavelength times frequency, right? Think of the units here. The units make sense, right? Frequency is 1/2, wavelength is meters. Multiply them together, you get meters per second. Okay, so everything in this chart is related by this relationship here. All right, the frequency, well, it depends on what's creating what's oscillating at what frequency and creating the electromagnetic field. And then the wavelength that it has is going to depend on its speed, where in vacuum is c. Okay, but we will deal with situations where we're not in vacuum, and so its speed won't be c, and therefore its wavelength will change. All right, so let's look at this spectrum here. Professor Anderson does a really nice video on it if you want to watch that. we have our radio wave, okay, our 60 hertz all the way down here, right? 60 hertz AC current that we use in our houses and things. That's all the way down here. Microwaves, visible light in the roughly 10 to 15 range in frequency. And then up here, super high frequency, you get gamma rays. And basically, electromagnetic waves that come from deep space is high frequency. So what's really interesting about this spectrum, let me just kind of delete this stuff real quick, is I don't know if you've heard of particle wave duality. It's basically a concept that many objects that we kind of can predict or describe their motion, they can be described equally as a particle or as a wave. In an electromagnetic spectrum, the stuff on this side is best explained by wave theory. The stuff on this side is better explained as a particle. Even though they're all waves, right? They're all electromagnetic waves, but objects that, oscillate at a frequency at light and below her, visible light and below her, are better explained as waves. And then really high frequency objects are much better explained as particles. It's just one of those, really interesting, that can get really philosophical very quickly. So we'll be talking mostly about stuff on the left-hand side. So wavelength and frequency related by the speed of light, and the speed of light is in a vacuum is 3 times 10 to the 6 meters per second. So this is a very interesting video on color. I didn't talk too much about color yet. We're going to get to that when we get into optics. But here it's a very neat video to watch because color is arbitrary. That's what I'll just tell you. Color is arbitrary. Red doesn't have a specific wavelength associated with it. It's completely arbitrary, and it's not super arbitrary, but it has to do with the instruments that we use to see color, which is our eyes. And everyone's eyes are different. Some people are colorblind in certain areas, right? And so this assigning color to a frequency or a wavelength is super arbitrary in that way. All right, so it's kind of like a spectrum, and you can see how it's kind of blurry here. But it's an interesting discussion nonetheless. So watch that video. So the next thing I want to talk about is let's talk about these electromagnetic waves as waves. There's a couple of different forms of waves, and there's two in particular that explain electromagnetic waves pretty well. The first one is a plane wave. So what is a plane wave? A plane wave is simply a type of wave where the magnitude of the E field and the B field is constant over a plane, okay? A plane in 3D space. So for example, the amplitude of this electromagnetic wave is equal anywhere in this region right here, okay? So, and then at certain planes, so maybe this plane, it's also a max, all right? And then at this plane, it's also a max, and in between, it's 0, okay? Anywhere outside of the plane, the amplitudes are 0. And this is just a type of wave. It's just a wavefront. It's just a way to very simply describe an electromagnetic wave mathematically. And so here are some properties of plane waves. And it also extends into sinusoidal waves as well. So the first property is that in vacuum, okay, the magnitude of, at any point in time, the magnitude of the E field is equal to speed of light times the magnitude of the B field. So if you know the E field at one point in time, then you can figure out B, okay, and vice versa. And we can also express the magnitude of the B field in terms of E, all right, where The B field is basically all these constants times E. So you have two different ways to find the magnitude, okay? And so finally, if you kind of combine these two equations together, what you see is C. And we kind of did a previous example when we were, I think it was in sources of magnetic field section where we saw this equation, we found it. And basically what it's saying is that the speed of any electromagnetic wave in vacuum, you can see how it's universal. It's equal only to 1 over square root of the permittivity and the permeability of free space. Okay, which there's no frequency in there, there's no wavelength built in there, right? Doesn't matter what the source of that electromagnetic wave is. If it's in vacuum, it is traveling at C. Okay, it doesn't matter if it's from, the source being a 60 hertz source or a 10 to the 20 hertz source, okay, it will travel at the same speed if it is in vacuum, all right? And so here's all those constants. 10 to the 8, I don't think that's right. 10 to the 6, sorry, typos here and there. Is it 10 to the 8 or 10 to the 6? I think it is 10 to the 8. I think up here is where I wrote it wrong. This is where I gave you the wrong. Alrighty. So this is basically a simple plane wave can pretty well describe an electromagnetic wave in vacuum, okay? So that kind of gives us the magnitude of the electromagnetic wave. What about the direction of the electromagnetic wave? So E and B are coupled together now, right? We're describing now E and B at one point in space. And the E field is going to always be perpendicular to the B field. So that is going to be the plane, right? That's the plane of the plane wave. And the direction that the plane wave travels is always perpendicular to the amplitude, the plane that describes the amplitude. So this is basically giving you another right-hand rule to go off. So E cross B, right, the plane created by E and B, the propagation vector will always be perpendicular to that plane. So if you sweep E into B, your thumb will point in the direction of propagation. So that's kind of a final right-hand rule that we'll probably talk about in this course. So a pretty simple one, right? So the direction that this wave moves is perpendicular to both E and B. So let's look at this conceptual problem and let's kind of practice that right-hand rule. Find the direction of the B field in each case. So part A, we have the wave propagating in the positive Z direction, and then the E field is in the positive X direction. And we know that E cross B equals V. So that means that our X hat cross what is going to give us positive Z. Well, that one's a pretty easy one. If you go clockwise in your cross product, your result is positive. So X cross Y would give us Z. So our B field must be in the Y hat or the J hat direction. The wave is propagating in the Y direction, and E is in the negative X. No, sorry, negative Z. So let's go back over here to my little arrow here. So I'm crossing negative Z with what would give me Y. So I'm going to drop the negative for now and bring it back in later. So Z cross what gives me Y? So Z cross X would give me Y. And it gives me a positive Y if I go this direction. So my answer for Z cross what gives me y would be x, but since I have a negative sign in here, I'm also going to have a negative sign on this side, right? So the B field would be in the negative x direction. So basically the technique here is to kind of like pull out your negatives and then bring them back in later once you figured out the cycle, okay? And they're just a negative sign, so you can multiply them in and take them out whenever you want, as long as you keep good track of them. So for part C, we have the wave propagating in the negative x, and then our E field in the positive z. So we are answering the question, z cross what gives me negative x? So we need a y in there, and the question is this y positive or negative? So when we go counterclockwise in our cross product, okay, counterclockwise, which, for example, z cross y is counterclockwise, our result is negative. So what this is saying is that z cross y is a negative x. Well, if we have instead z cross, oh, that is just z cross y. That's what we have. There we go. Z cross y gives us negative x. So I was thinking if the y was negative, what would happen? Okay, which is a good, go through that too, because this could end up on an exam, and this would be a great way to test, every possibility for this question. Let's do this question first, and let's answer the one that I just brought up. So z cross what gives you negative x? Well, that's y. Z cross y gives you negative x. We didn't have to do anything else with our signs. So I guess now what if V was in the X and E was in the Z? Okay, this will be, we'll call this part D, which is the part that I'm making up. Where you're going to run into, you're going counterclockwise in the cross product, and you have an extra negative in there. So like I said before, right, what are we solving? We're solving Z cross what gives me positive X. So we know there's a Y here, and we know that Z cross Y gives you negative X. So in order to get a positive X, we would cross it with a negative Y, right? So that means if that is true, then this is true. Oops, X, right? My hats. So then B in this case for part D would be negative Y, okay? It's the same kind of stuff we did in the previous chapter for the right-hand rule. This is all right-hand rule stuff. Doesn't matter what the application is, okay? It's still the right-hand rule. That's how we deal with it. So this is also a great video. I recommend you watch all these Anderson videos. They're all really good. He's basically here describing this propagation that I was talking about, how electromagnetic waves move in space on their own. And that's because of this endless cycle of changing E creates B, changing B creates E. So we talked about plane waves, all right? What's going to be a much better way to describe an electromagnetic wave, a little more specific, is describing these waves as a sinusoidal wave. And so we can use all the properties of plane waves in conjunction with describing E and M waves as a sinusoidal wave, because when you're very far away from the source, okay, of the wave, when you're very far away and you're looking at just a small area, it will still behave as a plane wave, okay? So we can then add these extra components of a sinusoidal wave properties in this small little region very far away from the source. So electromagnetic waves are sinusoidal waves. It's just how you would imagine. The E field is going to vary as a function of a sinusoidal function with time, and so will the B field. And they're going to max out at the same time, okay? So wherever you have the maximum E field, they're going to have the maximum B field. Wherever they're zero, they're going to be zero, okay? So they're both going to have the same function, except their amplitudes will be different, right? One will be describing E and one will be describing B. So, and then also the other thing that's different is their direction will be different, right? They always have to be 90 degrees from each other. So the E field would have only maybe a Y component, and the B field would have maybe only a Z component, and therefore the direction of travel would have to be X, okay? So let's take a look at what these waves look like traveling, okay? So if this wave, this E and M wave, is traveling in the positive X direction, that means the vector E cross B would be pointing in the positive X. And if this wave instead was traveling in the negative X direction, well, then E cross B would need to be equal to negative X. And that's the same as saying B cross E. So B cross E would equal positive X, and E cross B would equal negative X. Okay, so if you were to flip them, and that's why you see their positions change, you can see the B field is, ahead, if you will, right? So if you cross B into E with your right hand, you get positive X. But if you needed to cross E into B, which you do for the right hand rule, that would give you negative X, the direction of travel. So this is going to be the functional form of a sinusoidal electromagnetic wave. It is a cosine function, okay, and then we have some constants and things in there which will look familiar if you have analyzed waves before, right? K is a wave number. This is how they're all related here, actually. But K is the wave number, and it's related to the wavelength. It's basically the angular wavelength. And then omega is the angular frequency, okay? And when you multiply or divide them, you get C. And then when you multiply lambda and F, you get C as well. So that is how they are all related. And this particular equation right here with the minus sign in it is telling you that the wave is traveling in the positive X direction. And so that's definitely a little counterintuitive for most students. You're like, well, why is this negative if it's traveling in the positive X direction? I have a video actually to show you that. It's just the nature of how we describe traveling waves. So let's watch this video real quick. And what you can see, this is going to be a function plotted. And what's changing is the term on the right. It's increasing negatively, right, from 0 to this negative 0.6 pi. And take a look at that. Let me just swap back to this, right? That's the minus omega t right here. All right, and let's see how this minus omega t as it
Inside
gets
of the
bigger.
cosine, the blue curve is plotting the result. And as I continue increasing this number, you can sort of see the wave sliding to the right. And if you put your thinking cap on and really just like visualize it, if I drag my mouse with a constant sort of speed, then you can imagine this as being a propagating wave going to the right. And that's exactly what it is. Now, I'm going to show you how to write that down in a minute, but that is the reason we learned this, to be honest with you. So look at what's going on. As you
Okay, so you saw that, right? You're fully convinced that as you basically subtract more omega t's, you have a wave traveling to the right, which we typically call to the right positive, right? And if you were to instead add omega t's, you would be propagating to the left, which we typically call negative direction, okay? So that's going to be important when building these equations and when you find the direction of travel, if it's positive or negative, you need to remember to include the proper sign here in the cosine argument. So the same as a plane wave, the amplitudes are the same, okay? Amplitudes are still related by c, the speed of light. And so let's do this example here where we're going to take all this information and build these equations up here. So we have a carbon dioxide laser emits a sinusoidal electromagnetic wave that travels in vacuum in the negative x direction. So V is in the negative x direction. The wavelength 10.6 times 10 to the minus 6 meters, right? That's a micron. And then the E field is parallel to the Z axis. And E max is 1.5 times 10 to the 6 voltmeters. That's mega. So write vector equations for E and B as a function of time and position. So let's just copy down the ones that are up in the previous slide. That's a vector. Cosine kx minus omega t in some vectorial direction. Okay, which I'll just call like, E r hat. That doesn't really mean anything other than it's just the unit vector for whatever direction E field is. And that's actually what we need to figure out. But these are just the placeholder equations that I'm writing. Okay, these are specifically for a certain situation, right? When the E and M wave is traveling in the positive x direction. So E per path. Okay. So let's kind of like, what do we need to probably figure out what this is, plug it in. We need to figure out what direction it's traveling in. We would replace basically the minus sign and the x here. We need to figure out what k and omega are, and then we need to figure out what direction. So we have a lot of blanks to fill in here. So to start building the equation, we can start right here. We know that it's traveling in the negative x direction. So our E and B field are going to be functions of x. So we know that much. We're going to figure out E max and B max. Now let's figure out what the directions are. So if E is in the z hat direction, we're going to have our cosine argument plus omega t, right? Because it's traveling in the negative x. And then this would be in the k hat direction. And so this would be cosine kx plus omega t, right? Because it's traveling in the negative x direction. And let's see, k hat cross what gives me I hat, negative I hat. So we would be going, let's see, x, y, z, I, j, k. That's z cross y would give me negative x, right? Because I'm going counterclockwise. So this is in the j hat. And so now let's find E max, or let's find B max, K, and omega, right? To fill in all the blanks. We know what E max is. So B max would equal C E over C. All right, so we would have that number. And then K would be our next unknown, which is 2 pi over lambda. I'm sorry, lambda over 2 pi. It is 2 pi over lambda. Did I write it wrong up here? I did. Sorry about that. I catch myself sometimes, catch my mistakes. So 2 pi over lambda. And I knew that. I checked myself because I know the units of K are inverse meters. So I knew lambda had to be in the denominator. And it also makes sense because multiplied together, they equal C, right? So if this is, it's lambda over, lambda over 2 pi. So hold on. Omega is 2 pi F. K is lambda, 2 pi over lambda, right? That puts the lambda in the numerator, and the 2 pi's cancel, and then you're left with this. So you can always, double and triple check your units and your relations here in case you get a little mixed up, like I do. But sometimes when you rely on memory, it's like your brain will just flip the two numbers. So 2 pi over lambda, okay, we can get that number easily because we know the wavelength. And so finally it's time to find omega. So I'll write that in red since I was writing my unknown. So then omega, well, would be equal to, we can use this relationship here, C times K, right? We know C, and now we know K. And now we can plug all those values in, right? We're going to plug in K, omega, B max, and we're good to go. So I'll let you work that out numerically, but this is kind of the skeleton, and this is definitely a question that would appear on the exam, very typical exam question. In the homework, I believe there's some other variations of this that you can practice on, and same in the practice quizzes.
Okay, so now what if the electromagnetic wave is propagating in some kind of material? Well, what happens is the wave slows down when it's in a material because when you're in a material composed of atoms, orbiting electrons, and you will get an interaction between the E field and those objects, and that E field will lose its energy. Okay, so it won't travel as fast as it does when it's in vacuum, when it has nothing to interact with. And so the speed then, you should imagine, the speed would get smaller than the speed of light, right? So the speed of light divided by these two constants, K and Km, which are the dielectric, you may remember K is the dielectric constant, and then Km is just the relative permeability, and they're related, they're just the ratio of the permeability to the permeability in vacuum, okay, and vice versa. So this number combined, okay, square rooted, is going to give you some kind of positive value greater than 1. And so anytime you are traveling in a material, your speed is going to be c, the speed of light, divided by some number bigger than 1, which is going to, of course, reduce the value of the velocity. And so you can express this in a couple of different ways, okay, just by using all these relationships here and the relationships from previous slides. So there's a couple of different ways that we can write the velocity of an electromagnetic wave in a material, in matter. And just as kind of like a foreshadowing, we'll be talking about this index of refraction a lot. This index of refraction is a number that is related to, it's basically the ratio between the speed of light in vacuum and the speed of that same wave in a material that's not vacuum. That gives you the index of refraction n. Well, the index of refraction n is also equal to the square root of kk. All right? So in this example, we're going to kind of use that idea. So let's say we're in a jewelry store and you hold a diamond up to a lamp, a sodium vapor street lamp. And so the idea behind the sodium vapor street lamp is that it emits one frequency of light, okay? And that's 5.09 times 10 to the 14th. So what is the wavelength of that light in vacuum? And what is the speed of that wave and its wavelength in a different material like diamond? Okay, so what we know is that this, the frequency of the light is 5.09 times 10 to the 14 hertz. And what is the wavelength in vacuum? Well, we know that the speed of light in vacuum is c, and that is equal to the wavelength times the frequency. So we can solve for the wavelength of that light in vacuum as c over f. And that becomes 3 times 10 to the 8 meters per second divided by 5.09 times 10 to the 14 hertz. Right? And that gives you and make sure you use parentheses in your calculator if you're typing it all in at once. That could be a source, a common error here. 5.89 times 10 to the minus 7 meters, right? Wavelength is a meter, units of meters. So that's roughly 589 nanometers yellow light, right? If we scroll all the way back here, that's yellow light. Sorry to close your eyes while I scroll quickly. There we go, right? Yellow, between 550 and 600. So that's yellow light. And there we go. Now, what color is it when it's in diamond? All right. What is the wave speed and the wavelength in diamond? So the frequency stays the same. Okay, the frequency is a property that doesn't change just because it's in a new material. So the frequency in diamond is still going to be 5.09 times 10 to the 14 hertz. But now we want to know how fast is it traveling in diamond, given that the permeability and dielectric constant are this. So the speed then is going to be, we'll go back up here, C over square root of KK. Oops. C divided by the square root of 5.84 times 1. So it's going to go a lot slower. And now that we know that speed, which is 1.24 times 10 to the 8. So about third, it shrunk by a third, right? It's 1 over square root of 584. 5.84 is 0.4. Okay, so it shrunk, by, basically 4/5. It's roughly a third. And that's the velocity. So now we can figure out the wavelength of that light now that we know its velocity. So its wavelength is going to be its velocity times its frequency. No, times. I think it's divide, right? Sorry. It's going to be divided by frequency. There we go. Divided by the frequency, which stays the same because the frequency doesn't change. All right, and you're going to get a wavelength of 2.43 times 10 to the minus 7 meters. That's about 243 nanometers, which is in the not visible spectrum. Yellow light is gonna shift into an ultraviolet light when it's traveling in a diamond. So in part B, we're going to kind of do the same thing, except we're going to be, instead of talking about light, we're going to be talking about a radio wave. I'll let you do part B. Same procedure here. So let's talk about the energy that's stored in an electromagnetic wave, right? So I told you before that electric fields store energy. We were talking about how magnetic fields store energy in inductors, right? Well, so electromagnetic waves store energy as well. And because we're talking about a wave moving through space, it makes sense to describe the energy that waves carry as a transportation of energy from one place to another. And so we use the Poynting vector S to describe this movement of energy flux, this direction of energy flux, direction of energy transfer, okay? So the Poynting vector is going to be in the same direction as the velocity vector. And so all we're doing here is E cross B, but we're having a small constant in front of it. Okay, so the units then become an energy per unit area, per unit time. So this is the Poynting vector. It's just simply the E vector cross the B vector. Okay, 1 over square root of that. 1 over divided by the permeability. And it becomes useful when we want to talk about the intensity of a wave. So intensity is an average value of the electromagnetic wave over a certain area, right? Because this electromagnetic wave, it's a time varying wave. So in order to make some sense of that, we need to average it over an area and over a time. And that's going to give us intensity. And so when we average these two E field vectors, okay, the E field and the B field vector, we're averaging a cosine function, and the average of these two cosine functions gives you a 1/2. Okay, so that's where this 1 over 2 comes from. That comes from the average. And then the EB over mu naught, well, that's just the magnitude of that Poynting vector, right? It's just E times B times sine of the angle between E and B, which is 90, which makes it 1 divided by mu naught, all right? And so we can use all of our different expressions for E and B. We can plug those in and get a few other versions of the intensity of an electromagnetic wave, all right? And so let's recall what is intensity. So remember, intensity, here's the units, right? It's a watt per meter squared. So watt is an energy per unit time, and then an intensity is an energy per unit time over an area. Okay, so that's an intensity. So you need to know what area this field is spread over, okay, in order to calculate intensity. So let's do this example here. Let me erase all this. So intensity, all right, well, let's read the example first. So we have a radio station, and it's located, right here. And a radio station on the Earth's surface, let's say that it emits a sinusoidal wave with an average total power of 50 kilowatts. Okay, so right here, we're sending out 50 kilowatts of E field, okay, in all sorts of different directions. Assuming that the transmitter radiates equally in all directions, okay? Assuming that, what is the electric field and the magnetic field amplitude detected by a satellite which happens to be 100 kilometers away from the antenna? So this is where we need to recall. So we'll obviously, right, we're going to be using this equation up here. Okay, intensity equals some form of E and B, all right? So what is the intensity? So we're going to need to figure out what the left-hand side is. What is intensity? Well, intensity is a power over an area, okay? What's the power in this case? It's 50 kilowatts. What's the area that we are concerned with? It's the area of this hemisphere, okay? So the area of a sphere, the surface of a sphere, is 4 pi r squared. So then the area of a hemisphere would be the area of a sphere divided by 2, right? So our area is 2 pi r squared. I'll change to little r here since they use the little r. And so we can figure out the left-hand side because we know the parameters that give us the numerical intensity. And so it's going to be 50 kilowatts, 50 times 10 to the 3 watts divided by 2 pi 100 kilometers squared. So, let's calculate that. Times 100 times 10 to the 3 squared. Oh, and parentheses. And so we get an intensity of about, I'll just round it to 8 times 10 to the minus 7 watts per meters squared. Okay, pretty small intensity, but the sensitive, detectors and satellites can easily pick up something like that. And so, well, that's going to be the left-hand side of our equation. The right-hand side, we know that the intensity is the average of the Poynting vector, which is going to be EB over 2 mu naught. But we need to find E and B, so we should just find one first, right? Because here we have 2 unknowns and 1 known. So we can use the expression E squared, just make sure I get all my E squared over 2 mu naught C to find E max. So it's going to be equal to I times 2 mu naught C square root. And that's going to give us E max. So we plug in our values there. Times 2 times 4 pi 10 to the 7 times 10 times 3 times 10 to the 8 meters per second. Whoops, that's 10 to the minus 7 there. There we go. And so we're going to get, let's see, and we get 0.022425 voltmeters. And so then we can figure out what B max is, because we know B max is equal to E max over C. So then we take our E max divided by C, and you get a magnetic field amplitude about a pico, a little bit more than 8 picotesla. So basically that's how you would approach that problem, right? You use your ideas that you learned from Physics 1 about what's intensity. It's just simply a power over an area. So you need to know what area we're talking about. And then the right-hand side would be all of your properties of your E field and your B field. And so the last thing we want to talk about when we are thinking about electromagnetic waves in terms of sinusoidal functions is what happens if we were to trap an electromagnetic wave in a cavity. So recall that electric fields do not exist in conductors, right? So if you have a conductor, the electric field inside of a conductor is always 0, right? So if we have a traveling electromagnetic wave, and when it's traveling, the E field and the B field are in phase, right? The cosine functions are the same for each one, right? Blah, 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 cosine K, kx minus omega t, right? Blah, 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 cosine, they're in phase. However, when you trap a wave in a cavity, the electromagnetic wave, which is composed of both B and E, well, when the E part sees a conductor, right, it's basically seeing a brick wall. And it cannot, let me make my 0 here, right? It sees a brick wall, and the E field bounces off of it, right? Because it can't exist in that material. It can't exist in a conductor. But the B field just keeps going on its merry way. And so what happens is in the standing wave, let me make sure I draw it right. Go to maximum. In a standing wave, the E field is 0 at the walls of the cavity. And then the B field has a max at the cavity. And it should be 0 when E is a max. And then it will be like this. So, oh, wait, no, see, it's hard to draw it. We're drawing it basically half a wavelength out of phase, right? So wherever E is a max, B is a min. Wherever E is a min, B is a max. There we go. Cross is 0 here. And then max is here, and then cross is 0. There we go. There we go. So they're no longer in phase anymore when they're in a cavity, when they're forming the standing wave pattern. Okay, E and B are out of phase. The nodes of E occur at the antinodes of B, and vice versa. Okay, so the nodes of E are when E equals 0. Write that in red. So when E equals 0, that's a node. Okay. When B equals 0, that's a B node, but the other wave has its max at a B node, and vice versa, right? And the B field has a max at a E node. And so this is a GIF that if you're looking at the PowerPoint, you will see what this GIF here, which doesn't work now in the PDF version of this, it's showing you a traveling wave. So the blue wave is a traveling wave to the right, and it hits a wall, turns around, travels the other direction, and what you'll see is that those two waves, when you add them together, they add constructively. All right, so you're going to see a max occur, and a min occur at the peaks. So, so standing electromagnetic waves behave the same way as a standing mechanical wave that we learned about in Physics 1, except now we have two components of the wave to worry about. We have B and E to worry about, and they are no longer in phase. They are out of phase because when they encounter a conductor, the E field cannot exist in a conductor, and therefore it reflects off of the boundary of the conductor and turns around, travels the other way. And so then you get these left and right traveling waves adding up constructively into a standing wave. And so standing waves, the wavelength that's set up in a standing wave, well, there are certain multiples, and it depends on the length of the cavity, okay? 2 times the length of the cavity over the number of nodes. So, and then the frequency you can figure out the same way. That's just C over lambda, okay? That'll give you the frequency. And that's, of course, if we're in a vacuum. So where do standing waves come into play? Well, when we heat up our food, we're creating standing microwaves in a cavity, the cavity being your microwave. And that's why when you touch the walls of your microwave here, it's metal, it's a thin metal, right? And that's because we want the waves to bounce back and forth inside this cavity, creating a standing wave. And so wherever you have the antinodes of the standing wave, you're going to have areas of maximum magnetic or electric field, and that's going to heat up your food by interacting with the water molecules in your food. And then wherever you have no wave, you're going to have no heating. And so we need to rotate our food in order to hit, all the places in the food equally. So the wavelength then that is set up in the microwave is going to be equal to 2 times the length of the microwave over the number of nodes. Okay, so if we have nodes spaced 6.1 meters apart and the microwave is 12 meters in length, then we would have only one node. Okay, so let's look at this example here. And in this last example that we're going to do, we have electromagnetic waves set up in a cavity, okay? And the cavity has a length of 1.5 centimeters. What is the longest wavelength and the lowest frequency of these standing waves? So we know that the wavelength that's set up in this standing wave pattern, the wavelengths that can exist are equal to 2 times the length of the cavity divided by the number of nodes. So to get the longest wavelength, we need the lowest number of nodes, which is 1. So the wavelength then would be 2 times 1.5 centimeters divided by 1. So the wavelength of the largest wavelength in that cavity is going to be 3 centimeters. And so then what would the frequency be? Well, the frequency would be, we could find that out because we know that these waves travel at the speed of light, and that's equal to their wavelength times their frequency, right? So the frequency, we can solve for that, and it's just c over lambda. Use your SI units. And so basically we get 8 and we get minus 2. So that becomes 10 to the 10. 10 to the 10 hertz. So, all right, so for a standing wave of this wavelength, okay, so for this standing wave where n equals 1, where in the cavity does E have a maximum? Where is E 0? Where does B have a max? And where is B 0? So let's draw our cavity. So here's our cavity. It's 1.5 centimeters, okay, not drawn to scale. And we have one node in there, okay? So we have one node, which means we have a wavelength. All right, so if we have one node, that means our wavelength is 3 centimeters. And since we only have 1.5 centimeters to draw a 3 centimeter wavelength, we're only going to be drawing half of the wave, right? So for an E field, let's draw the E field first in red. And let me kind of draw like a 0 line here. Okay, just so we can see the 0. So we're going to draw half a wavelength, and we know that the E field at a conductor is 0. So the E field must be 0 at the conductor. And we're drawing half of a wavelength, right? That's half of one, right? This would be a whole one. But we're only drawing half because the cavity is only 1.5 centimeters wide. And that's the E field. Now the B field, remember, is out of phase now, because the E field gets reflected at the boundary and the B field doesn't. So the B field has its 0 wherever E field is a max, and it's going to then have its max wherever E is a min. So if we go up here, boom, that would be the B field. Okay, so this is halfway. And so the E field is going to be a max at 0.75 centimeters. The E field is going to be 0 at 0 centimeters and 1.5 centimeters. And then the B field max will occur at 0 and 1.5 centimeters. Well, I mean, you know, the max, I guess, it's the max amplitude, right? Even though it's negative. But it's still, the amplitude is still a max. And then the 0 B will be 0 at halfway point, 0.75 centimeters. Okay, so that's because we're dealing with one node. N equals 1, which is half of a wavelength. I mean, half of, right, 1.5 is basically, you can only fit half of a wavelength in there. All right, so that ends chapter 32. It's not super long. We're just basically characterizing waves, electromagnetic waves. We learned how they behave in cavities, right? E fields reflect off of conductors. So because they cannot exist in conductors, their value is 0 at a conductor. Okay, and so therefore the E field and the B field are no longer in phase. But if the E field and the B field are traveling together in outer space, not near any conductors, then you see that they are in phase, right? They're in phase because look at the arguments of the cosine, they're exactly the same. All right? And so then we learned how to write the E field and the B field in terms of vector, sinusoidal vectors, okay? The relationship between E and B and the velocity. So it's really, you know, I think it's a bit of a breath of fresh air compared to all the crazy right-hand rules we were doing before. This is going to be very easy to digest material. So go over these examples, go over the stuff in the practice quiz, okay? And just try, you know, every different variation of these problems and also the example problems at the end of each chapter. Okay? Next up will be chapter 33. We'll start talking about light.